Creo que no habíamos hecho nada, pero yeah.
Okay, so as we have, okay, close the door. So we have solved the technical issues, and I can properly introduce my friend Ivan. Actually, besides a great researcher and a fantastic engineer, because his undergraduate was in electrical engineering. Actually, we know each other for 30 years. Almost 31 years. And at some point in his life, he decided he didn't want to be an engineer, and he wanted to learn physics. And then at that point, I was moving to Australia. So he said, okay, why don't I go with you and I learn physics with you? I said, okay, you can come, but I don't know how much are you going to learn with me. Anyway, he learned something, but now actually he has excelled, and he did his PhD with me in Australia for 3 years and a half or 4 years. And then he moved to Germany, to the Karlsruhe Institute of Technology. And now he's working there now for 10 years. He told me time flies. And he's working in a variety of let's say, numerical and algebraical techniques, basically for photonics, but also for other fields. And he's going to tell us a little bit about that. So thank you, Ivan, for coming. Thank you for maybe we should stand here. No. All right. Thanks a lot for the introduction, Gabriel. And it's a pleasure to come here. I've been a couple of times, but I never visited the centers. There was conferences and so on. And yeah, so exactly. So what I do is I try to use theory to find computational strategies to compute light-matter interaction. And I changed a little bit the outline of my talk. I wanted to go into some more quantum stuff at some point, but I heard that there is a strong interest in DFT and molecules and systems in here, so I put more emphasis on that. It will be two distinct parts. The first one, about molecular materials,
And obviously one has to reach some scales when you do that. And the other one will be a more abstract part where I'll show you that one can generalize this typical D-matrix transition matrix. I'll explain what D-matrix is. From monochromatic to polychromatic, and also extended to matter, to static matter. Right. But this will come in. I don't know where I'm stuck here. I don't know. Okay. I really like this slide, and so I copied because it shows that human civilizations are also marked by the materials that one can use and mold. Okay, so you can see names that you're familiar with. Okay, I find it very interesting that they use silicon for the information age. I find it very suitable. And here downstairs, you see the engineering processes that you need to mold these materials. And as you know very well, here, now we are in this one where we can do micro and nano fabrication, and we are very able to structure matter at almost the atomic scale. So if you also see, the other thing that I like about this is that you see the duration of the different ages, and it keeps reducing and reducing. So it's like we are able to make materials, new materials faster and faster. But sometimes you make the materials, but you don't know what's going to happen to them. That's actually an interesting problem. And I'm going to talk specifically about optical devices that contain molecules, and they will be in two forms. So either some kind of dispersed random solution of the molecules, such a solution in liquid, for example, or a crystal. In TIE, there is groups that one particular almost institute that are specialized on what they call metal organic frameworks. So the idea is that the organic ligands will attach to metal ions, and they build up these scaffolds. Okay, here's a picture. Okay, so they can make films out of this, and also sometimes they crystallize in some beautiful shapes, including the fact that in these ones there are two MOFs, one inside and one outside. So this is a more complicated matter. Why are they interesting? At least that's what they say. It's because you can pretty much do this with any organic ligand, and then hence there's going to be strong light-matter interaction. So maybe you can play some games for the effects that you're looking for. And one other thing that experimentalists really like to do is to put molecules inside cavities. And the idea, okay, of course, is that there will be some enhancement of the light-matter interaction. In particular, one can say that light is a long time in a cavity mode, with a lot of passes through the matter. And then you may be able to enhance the sensing of molecules that you put inside, or enhance the optical effect of molecular materials. Also, there's been maybe some of you, I'm sure, are aware, there's some recent ideas that if you have a molecular reaction inside a cavity without illuminating the cavity, this can be different than what happens outside the cavity, which is, of course, a potentially very interesting application. And this is what's called proprietary chemistry. However, recently, there's been some questions whether that's what's going on. I'm not going to explain this, but I know some of you are familiar with this. That one should look also at other places, not just the polarities, for trying to explain this so far unexplained changes in the cavity, for example, the reaction rates. All right. Now, I'm a theorist and interested in doing models, doing calculations. And one wants to do, in a system such as this and this, joint optical response of molecules per time. How do we do this? This was actually the problem that they came to us with, the people that were making these MOFs. They don't know how to compute the response. So you need it to be accurate, of course, to be able to predict the measurements, but also efficient, so that one can potentially use this modern techniques for computer-aided design. And you can see the challenge here immediately. is the scale differences. Okay, this is of course not to scale. From here to here, there is not just 2 unit cells. This is much taller, and then you have to bridge these scales from, say, atomic, basically molecular to device, and okay, I didn't know that it was so long. Sorry, someone said. And there is another challenge. I mean, we think this is a feature interdisciplinary, and it's always very nice to write that in the abstract or whatever. But actually, this is a challenge. Okay, so it takes some time to take chemists, physicists, and material science to talk together and get acquainted to each other's formalism, language, and units. Some stories about this. But this challenge, let's say, we overcame. And okay, if you want to model such systems, what you need is what Dominic did. So Dominic is now Dr. Corbaton. He's a student in the group of, and he did this efficient simulation of biperiodic layer structure. If you have a system that can be described by a stack of layers, like such as this one, they have substrate, the cylinders, molecular solution, cylinder, substrate, vacuum. Then the layers can be of 2 kinds. One is this isotropic and homogeneous lap, which is going to say how tall this is and give the material parameters. Electric, magnetic, and chiral, if it's chiral. And the other one is the periodic layer, so such as the cylinders or the molecules in that one. You need them to provide the response of the unit cell and the 2D lattice vectors. And with that, you can do the calculations very efficiently. So you can put dielectric disks, you can do metallic helices as unit cells, and you can put molecular unit cells. And by response, I mean the T matrix. This is the first time that this appears. And that leads me to explain a little bit where can it be seen, where the T matrix can be seen in Lyman interaction, how it appears. This is not a typical traditional way of explaining it, but this is the way. So you have a cartoon where there is an object, material object, there is incoming light, the 2 interact for a while, and now you have the outgoing. After this has been stopped re-radiating, then you have this, again, this outgoing beam. And the idea is we treat this with Hilbert spaces, and I'll give you some reasons why. So F and G are in the Hilbert space of solutions of Maxwell equations, and S is the action of the object that maps the incoming to the outgoing beam, and it's a linear operator in that space. Why to do this? Now, one reason, okay, now the T matrix appears, it's basically the same information as S. S is identity plus T. There is some, it's easy to write down, at least abstractly, expressions for things that are otherwise more complicated to compute. Okay. What I mean by that, for example, let's say you have an operator in the Hilbert space that represents energy, or momentum, angular momentum, helicity. It's always self-adjoint if it's one of these fundamental quantities, observable. Then you ask the question, okay, how much did it change? You know, the total value. So from before and after. So the only thing you need to do is this equation. Okay, so you have the sandwich using an appropriate scalar product, which I will speak about later. Input gamma minus output gamma. Gamma is a generic placeholder. And then the G is Fs. So then you get this equation. And it works for any gamma. This basically substitutes, or it's in place of doing integrals of the Maxwell stress test. The symmetries of the object are easily, the consequences of the symmetries are easily found in this setting. Not going to talk a lot about symmetries. And in terms of the T matrix, one advantage that it has is computationally efficient to couple objects. So I have the 2 objects, say the pointer and the bottle, and I have the T matrix of the individual objects, and then I put them together and I ask, okay, what is the T matrix of the overall object? This is quite efficient. And if what you have is a repetition of objects, an infinite system, periodic, then it's extremely efficient because you can sum these interactions, all of them, in the lattice using what is called the Evans summation. Maybe some of you know these tricks. but actually it makes it fast and accurate. And at the end, the matrix is a matrix. Okay, it's in your computer, it's a matrix, and it depends on, typically it's in the multipolar basis, so the basis of vector spherical harmonics. And so if it's the dipolar approximation, you get a 6 by 6, quadrupole 16 by 16, and so on. With some object inside your computer. Now you want to compute these two matrices, and if you have macroscopic objects, by that I mean a cylinder made out of silicon or microns or something, or a helix made of metal. Then there are many codes. You can Google this. There are publicly available codes using numerical techniques for solving Maxwell equations, finite elements, or the extended boundary condition method. However, because we want to do it with molecules, that needed one extra step. Okay? One need to bridge, in a sense, quantum mechanics to macro theory, and more precisely, the polarizabilities from quantum chemistry onto utilities. This is really conceptually, it's more a technical challenge than a conceptual challenge. It's kind of obvious that those polarizabilities have to be the dipolar matrix, but you gotta find the formula. So you find it, okay, you don't see it from, don't worry about it, just the formula, but takes the polarizabilities from quantum chemistry and maps it into the dipolar matrix. Okay. The T matrix to the dipolar approximation, which is typically completely fine for a small group of objects. How does it work? You do full quantum mechanics simulations on one. And then you ask the question, for example, okay, I want to know the response of 4 molecules arranged in this way, cross. And the response in this case is the circular dichroism. This is the differential absorption upon illumination with left and right-handed polarizations of light. And then for this system, which is not too big, you can still do the full quantum mechanics. You can do it, it takes long, but you can do it. It's this reference dashed. But if you take the T matrix of this one and then you orient it in a way, you put the displacements and the rotations appropriately to this, then that calculation takes really literally seconds, whereas the full calculation would take weeks. And now you pay a price. Okay, and you can get these lines. I'm not going into the difference into these two, but those are T matrix calculations. So you pay a price. Okay, but otherwise it's rather fine. At some point you pay this price because if the system is big enough, you are not finishing with quantum mechanics. So you have to, you're forced in a way. These are the postulates that do DFT. We are using density formula theory and TD DFT data. And this is our, let's say, workflow. What do we actually do? So if we want to have a crystal of molecules, the first thing is to do a periodic DFT to see where the atoms are going to float in the lattice. And then you cut off a chunk and you do the TD DFT on this chunk. This is what takes time. This is cheaper. You get those dynamic polarizabilities from the TD-DFT, and you apply the formula I just showed you, and then you get the T matrix, and then you put it into the code. If, on the other hand, you have a random solution of molecules, or molecules dispersed into a polymer or something like that, then you do, when you do it, you just use one molecule, DFT, TD-DFT, and the polarizabilities now, you make assumptions such as some kind of dilution, they're not too close to each other, to be able to come up with material parameters for isotropic material. So you're assuming that they are randomly oriented and not too close to each other. And then you can get this and again plug it into the simulation. Right, so I told you how we do things, and I tell you now two examples. One is crystalline and the other one is amorphous. That's the first one. It is silver mirrors and a Hilbert mod here, and this is for, so this is the energy of frequency and this is the absorption, and the 3 lines are for different thicknesses of the film, basically heights of the cavity. So this is 200 and 300, and the red one is 400. And I bet 99% of us would go look at this and say, oh, I know what's happening exactly here. There is a material node here, and at 400, it entered into resonance with the cavity mode, and it split into polar electrons, the upper branch and the lower branch. Very convincing. Okay, sure, and we can actually do the simulation. So now we do the simulation. This is simulations. This is just the film, the absorption of the film without the mirrors, as a function of the thickness and the energy. Well, you get some, at least, okay, there is more molecules and there is more absorption. Sure. Now you put the two mirrors. I think they are, yeah, they were silver and then different thicknesses. And then you see that stuff bends. The cavity here, this simulation seems reasonable. You may notice that there are two lines, kind of for each, say, cavity mode in a sense. And this is because this material is anisotropy. But I'm going to ignore that from now on. All right. Now you can do something else. You write yourself the modal equations for the, say, for the Fabry-Perot modes of this thing. And it looks like this. This is the L. This would be the mode number. These phases are the reflection, the phases of the complex reflection coefficients from inside the cavity with the molecules in it, which is something that you can get out of the simulation. And then, okay, you get the refractive index of the molecules here with some approximations I'm not going to talk about, but the idea is that, yes, it's through quantum mechanical simulations that prove this. And then you solve this equation very easily. So you did this in MATLAB. And then you get the mode lines for the thickness of the film and energy, and different modes, 1, 2, 3. And here you get the refractive index. That's for information. And then you overlay this picture into the absorption simulation. This is all calculation that comes from the simulation parameters. And then you put on top of each other. You should be, I would say, relatively happy of the coincidence. And then you cut up 400, because this was the 400. And then the result is surprising, because if you look at the energies where these two peaks are, roughly, you see here and here that they are from two different modes. And this cannot be textbook electronic split. These are just two different modes. It's okay, if you just do the measurements, there's no way you actually can tell that this is not the same mode. All right. Then we were encouraged by the referee to do an extra case. Okay? So we chose another one, in this case, a random case. So this is a polymer, and then there are blocks, these J aggregates of these molecules dispersed inside, random. And their measurements are, again, very, very telling. So this is the absorption, the black solid line of the film without the mirrors. And then they put them inside the cavity, and then you get this red solid line. And again, same. This is clearly a polyatomic splitting. With the same thing, in this case, indeed, it's cutting through the same joint mode. Okay. But then, when you reach at this stage, you look at this picture. You look at this picture. They're not that different, right? So what we did, like, okay, let me change from the nominal concentration that was reported in this work to 5 times that concentration. I have no idea whether this can be done in the lab or not, but in the simulation, it's changing a parameter. And then you see now more bending, so the refractive index is more dispersive. And you see this more bending, and now you could find, you could find cuts where you could easily get confused again. So I don't know. It's not. This is not the point to question strong coupling for either something. It's just saying, if you look carefully, sometimes there are surprises. This is what I've been told. What I've been explaining is in this paper, and this is Benedict, who's the first author. And there's another paper from Benedict, also the first author. And you look at the title, and you see that the main difference is the word non-linear. Okay. And yes, you can do pretty much the same thing that I just told you for non-linear stuff. Now it works from T to DFT. What you take is this, they call them the first hyperpolarizability. If any of you don't know DFT, I'm sure that you know what I mean. And then then you get a 3-index object, not a 2-index object, but a 3-index object, 2 incoming fields and the outgoing one. And Benedict calls that the hypercube. And basically, you can do exactly the same. There is no much difference. Some things are, of course, take longer, but the main concepts, lattice sums and so on, this is basically the same. So you put, in this case, what was this? Urea into a cavity. Just to see what happens. And okay, let me skip this one. And then you say, all right, this is going to be about second harmonic generation. You come in with the fundamental, and the question is how much of the second harmonic is going up and down the path. Okay, so these are urea. Urea is a well-known second harmonic producing material. And so the test was, okay, we have the cavity. We have two cases for the thicknesses. So this height, let's say. In one case, the cavity is not resonant at the fundamental, and it's resonant at the second harmonic. And in the other case, it's double resonant. And the question was, okay, how can we enhance the second harmonic by putting the cavity? All right, maybe not a surprise, but in the case where it's not resonant in the first frequency, then there is no enhancement. Okay, so the green lines is the enhancement of up and down with respect to not having the mirrors, with respect to just having it. And actually, you don't get an enhancement, you get a reduction. However, in the double resonant case, you see that, for example, the signal going down, say reflection, gets enhanced by a factor bigger than 10. And this one, the one going up, maybe 2 times. I would like to point out that this is for the field, and you would detect, of course, field square intensity. So the enhancement here would be of the like 2 orders of magnitude. So it's something probably that is worth thinking about. Okay. Besides doing simulations, there was one thing that always tickled my curiosity in particular, which is the fact that okay, SHG doesn't happen in center symmetric materials to the electric dipole approximation. But you can measure from slabs. And the typical explanation is, all right, we will put there, so the interface breaks the center of symmetry. That is very understandable, of course. And theoretically, we'll put their surface tensor there, sense by hand, to do the simulations. However, how do you actually predict these components? Not a clear way to do this. And people will do measurements and then fit some parameters. Question, is it needed at all? Of course, the answer is no, because otherwise I will not answer these questions. What you can do is the following. All right, you cannot simulate a bunch of molecules like in a surface of macroscopic size with DFT. It's not going to happen. It's too many molecules. But what you can do is this. So you have a part that you do quantum mechanics. This is where you expand the cycles of the computer. And the other things here that you see these dots, these are partial charges. So they can model blocks of positive and negative charge, so that at least the electrostatic potential that these ones see is kind of faithful with what happens. And then this is easy. I mean, this is very cheap to do. And then, of course, then to mimic a surface, the only thing you need to do is to not put charges. So you can do this. It's rather inexpensive. And you compute, of course, then the hyperpolarizabilities of this. And now it's going to give you an example with a molecule that I cannot even pronounce. But basically, it's a centrosymmetric material that there is no SHG at all in the bond. So these are 31 layers, numbered from 15 to -15. This one is 0. And so did these simulations. And the first thing is, A here is the charge density, some isosurface, of the center layer. Okay. This one, should not be any symmetric gradient because it's all completely symmetric above and below. And the other plots here, the other figures, are the difference of different layers, this chart different layers of plane mass surface with respect to 0. So see the first 1, 5, almost no see the difference. 11, you start seeing something, and then suddenly it's very different. This is where you can see the symmetry being broken. I mean, you cannot really see it with your eyes. I mean, actually, yeah, if you stare long enough, you would see that there is a displacement towards one side. Okay, and then you say, well, okay, now how does this produce AG? You can simulate it with, because now we have, let's say, hyper T matrices that are different for each different layer. And then we can put, okay, hyper T matrix 0 here, 1, 2, 3. So the margin did this. And then you can compute the generation of second harmonic in each layer. This is what happens. This is linear scale, this is a log scale. And what happened is basically that all the generation is pretty much in the first layer. Yeah. Okay, so don't get tricked. This is again modulus. I don't know how many times I've told them to plot modulus square, but there you go. So basically, this difference in order of magnitude you have to square. That's basically everything happens 15 and minus 15. Okay. And 0 is a, let's say, numerical 0. See the order of magnitude. Then you can start playing some tricks. And then, for example, Carson said, okay, we can put this. How do we enhance this? In a cavity, it's not going to work because you're thinking of the mode. It's occupying the whole layers. But if you put a curvature configuration and you have an evanescent wave traveling here, then you're gonna pretty much illuminate only the bottom layer and then enhance it very much. Turns out the story is not that simple. There is also a lot of generation of the top layer. But at the end, no matter, you can do a bunch of simulations, find also some optimal angle here. Of course, total integral refraction, but from that you can choose many angles that meet the critical angle condition, and then optimize the thickness to get enhancement. So say this is just the red lines are just the enhancement that you see, and now you can get enhancements which in intensity would be 3 orders of magnitude. Okay, here's the last slide from the first part. The code that I'm talking about, not the DFT part. But the other part, the whole thing else, is publicly available. I was going to just say, okay, so these are simulations that we did. I'm not going to explain them. It's basically, this is the optimization of a anti-reflection coating through a solar cell. And this is some chiral sensing inside a cavity. Point that I wanted to make is there is thousands of simulations in each of these pictures. And if you try to do this with console, you will not be able to. So this code is 100 times faster than console, including the time that it took to compute the T matrices of the different cylinders. Why is this? Why is this advantage? Well, one, because you're using the T matrix and Maxwell equations are solved for you already. Okay, and 2, these formulas for the lattice couplings that I mentioned. This is a Eval summation technique. Technique is very nice, and this makes it this much faster than most. I think this is actually a 500, but Dominic is very conservative. You can go in here, download trims, install it, and right, this is Dr. Golden. And okay, if you are able to just map your DFT results to the bipolar T matrix, you pretty much can do the calculations that we can. Now, switching gears, let me drink a little bit. So this is about to get a bit more abstract. So they said a few things already here. The one thing I didn't say, I'm going to say now. Say you want to maximize per energy per joule the amount of force, the force that you put to S to the. So you write down this way. You can at least write it down, and then later with the expression of the scalar problem, you can actually see what you have to solve, maximize it, and you will have the best speed. then you can go and try to implement that. Okay, but how do we do these calculations besides this abstract notation? Okay, what you need the representation of the fields and the scalar and the expression of the scalar product. One possible representation is the following: you have the electric and the magnetic fields, and you do these combinations, sometimes called Riemann-Silberstein. Although in those works, these are complex fields, and in those works, those are real fields. There's an important difference. And okay, so you have now these are helicity eigenstates. They are all circular polarized, either left or right. You can use them, or you can use their plane wave decompositions here. And you can represent the fields as these 6 column vectors. And this is the scalar graph. This is from the 60s, as far as I know. It's an integral in phase space. And if you got an average of something, energy, then you stick the operator in the middle, and then you need to know how gamma acts on these fields. Maybe more computationally convenient is when you have the expansion of the fields into multiples. This is a shorthand for a multiple of frequency given by k. J, it goes from 1 to infinity, j equal 1 dipole, 2 quadrupole, and so on. M going from minus j to j, and lambda, you can choose the helicity. You can also choose the electric and magnetic character of multiples, typical ones. Now, the scalar product looks like this. It's just all the different kinds of integrals and sums that you need. And for example, compute the energy when you have these coordinate functions, you have to do this integral, and then you get the energy. And this will give you the same as if you integrate over whole space e squared plus b squared. Zero epsilon accordingly placed. So it actually, of course, it gives the expected result. Now, I haven't explained this, but the P matrix has been until recently mostly considered for polychromatic. Okay, just one frequency in, the same frequency out. This we have generalized recently in something that is entirely polychromatic. Now, it is easier. Okay, you can say, well, we just do some Fourier transforms. Sure, you can try. Yeah, it's possible. I believe one can do it. It's just not easy to know where to put the factors of frequency, how to define the states so that things are nice. So to do that, you actually go to group theory and you ask yourself when things are invariant in the pointary group and so on, and you come up with some expressions. You redefine the plane waves by a frequency factor and so on. But I'm not going to explain those details. Bottom line, now you can do things such as this. I have a pulse, and I have a silicon sphere. The pulse has some energy. Like this I specified, okay, that the component of the pulse is the plane waves or the multipolar basis, and it has some momentum. What you compute now is very easily is how much energy and momentum was transferred from the pulse to the silicon sphere during the interaction. And compute for each pulse how much energy we're going to put in and how much momentum we're going to put in. So you can compute the force. You could do also torque, but for unless it absorbs, of course it absorbs. Only absorption will make it rotate. But you can do this now rather easily. Because of what I told you about the reference to the pointary group, now you go. So the boosts are now worked out into the formalism. For the polychromatic one, you have translation and rotations. And now for the monochromatic one, you have translations and rotations in the formalism itself. And now you also have boost. And now you can say, all right, let's see that I have the same object, not the same object, but suppose it's the same object, and I illuminate it with a laser from this light cell ideas that I don't know whether it's going to work or not. But in any case, you can now do the calculations for the same pulse and see like the transfer of energy, for example, as a function of the velocity of this. This is going away from the laser divided by c. You get some number, and you see, okay, you get some profile. You can do the same with momentum. How much force are you putting into the object? Again, the VOC. And then in this case, you could say things such as, well, when it's going already 50% of speed of light, then I have to change something because my transfer of momentum is dropping very fast. So you could use it for engineering. All right. Now, I got to the last part, the part of matter. I got to first say more things about this scalar product. This scalar product, or the other expression that I showed you, is unitless and it's invariant under the conformal group. So what is the conformal group? It's the largest group of invariants of Maxwell equations with sources, and it's composed by the point-carrier group. So that's, time translation, the 3 space translations, 3 space rotations, 3 Lorentz groups, so that's 10. And then you add stuff. You add dilations. Dilations is very easy to understand. You take space-time, TR, multiply by a positive number. This positive number is going to either shrink space or expand space. That's all. Easy. And now there are things that are, this is again, a 4 vector. And these are much more complicated to understand what they mean. They call spatial conformal transformations. I'll tell a little bit about them later. The point is they are in the group, and the point is that Maxwell equation resources are invariant. What does this invariant mean for the scalar product? What it means is that I have 2 fields and 1 transformation in this group. So this is, I call it C1531, 15 parameters, that's 4 plus 1 plus 10, and 3 space 1 time. I take this, any transformation in here, I'll apply it to the 2 fields, except, and now I do the scalar product between the 2 fields. Well, the invariance is this equal sign of this equal sign that is saying the transformed fields have the same scalar product as the original. Now, why is this important? For example, you can think of Zeldovich, I believe, was the one that said, well, actually, look at this. The norm square is the number of photons. So you can think of they have a mode F. Okay, let's assume it was normalized to 1. Now I multiply by something, so I get a bunch of photons in this boson mode. This is the number of photons. And of course, you need this to be invariant. It cannot depend on the reference frame, the number of photons. Otherwise, how can I quantize it, right? If I start moving inertially, then I'm going to change the number of photons. This is not true. So you need this scalar product to be invariant. Another thing, which is invariance, it allows you, it's important, or one could say, it's essential to define projective measurements. So there's a field, and here to the measurement apparatus. Let's say I have here a polarizer, maybe a monochromator as well, and then a photodetector. So this could be written as the projection onto a mode of light. In this case, probably a black wave. And this modular square of the inner product between D and G, G is the field to measure, and D is the mode of the detector. This is actually a unitless number, and it's the number of clicks of the detector. Again, you do not want that if I change both the field and the detector, so let's say the easiest case is I translate both, and you do the experiment again. Well, they better give the same number of clicks. More complicated examples is I boost both, but both at the same time. You see, you need this, that this is equal to this for the measurement to make sense, to not depend on the reference frame. I've been saying reference frame, which is the natural language for the Lorentz loop. But Castro made a series, there is a review on conformal transformations, which is very interesting. He says that the extra 5 transformations are better thought of change of reference units. And for the case of the dilations, it's actually obvious, right? I multiply by a constant number, space-time, so I'm changing the units of space-time. Think about it. And this change of units doesn't change. It's always the same in all space-time. So the best thing that I know how to interpret these transformations, the special conformal ones, is to say that this is also a change of units, but now it changes point by point. Okay. Again, it's not obvious to interpret what these things are. There is one way. To me, is the more clear one. What one should avoid is to confuse them with accelerations, because those is clearly not the case. And for that, you need to take a look at the paper from this side, this question. I think, okay, I'm going to use measurement frame. I feel like a mix between units and reference frame. So the measurement frame. So now we can ask the question that I wanted to ask from the beginning, which is, okay, can we extend this algebraic approach to matter? So we need a representative of matter, an invariance loop, and an invariance scalar product. So then we are in the same situation. And we're going to look for the representation of matter through the dynamic Maxwell equations. Here's a version that has the as a sources, the charge density and the current density, and also the magnetization density and the polarization density. These are say put together as a 4-vector and a totally antisymmetric tensor, such as the similar to the Faraday tensor. And these are put in a way that in the rest frame, I only get charge and magnetization, not polarization and not current. And this is reflecting the fact that you have electric charge and magnetic spin, and you don't have magnetic charge and electric spin in static matter. And if you find one of the two, then you get a trip to Stockholm. So we're talking about matter in static equilibrium. So hence before and after the Lyman interaction. So we put the J and the P to 0, and we put the time derivatives of everything to 0, because we are talking about frequency 0 now, and then you get a different set of equations, which are one version of the static Maxwell equations. So we're going to represent matter with rho and m, or better, with the Coulomb field produced by rho and m, so that there are two vector fields and not a scalar vector. Rho and E are bijectively connected by the divergence of E being rho and the curl of E being 2. And then we do the same thing for the group. We go to the dynamic one and we remove the stuff that we don't want. In this case, what is going to change our frequency 0 conditions that are removed. So basically the boost is C0 and P0, so the time translation is going to be identical, because we're talking about something that is static. So when you do that, you get another group. And that is some expression. I mean, you don't just remove stuff from a group and get a group. This just doesn't happen. But in this case, if you do it in this way, it actually happens. This is the steam parameter conformal group in 3 space. So you get that. And then you deduce what the form of the scalar product would be, inspired by the scalar product of the dynamic case again, and then you get it. You get this. Okay, so E of k and M of k are the Fourier transforms in space of rho and M. And then you have to show that this is indeed invariant under C10. This one I'm not explaining, but you can actually show. All right, and now you apply. Okay, so we have the same situation now as before for the dynamic case. So now we can do an example. So this is a magnetic field. This is the magnetization vector of a static magnetic configuration that is scalar. Okay. And they say, okay, you can stabilize this in simulations. And they say some people have seen it already, some kind of magnets. Some people, they say they don't, you have not seen it, doesn't matter for us. So I'm assuming rho 0 for simplicity, and now I can do sandwiches again. So one of them is, well, helicity. Okay, so I get a number, minus 129.1. I'm going to go into square, so I get another number. Okay, so my point is that the formalism for light and matter is now, for these calculations, is so similar that you can use some of the same self-adjoint operations. And in particular, this allows one to define the helicity matter, this thing that I just computed already. It was said that you could not do that, but the argument that they used for that was wrong. You can actually do this, and you find that when you do that, the helicity operator, this is the representation in K space, because when you apply to the field is 0, because this field is irrotational, then you learn that the charge density cannot store helicity. However, M can. This is why this is actually here there could be extra components of G squared coming from rho and put rho to 0, but here that should be the actual helicity of the whole thing. This suggests some experimental bounds. For example, imagine that you want to flip the handedness of this with light of any frequency. Well, whatever happens, you're going to need at least this amount of photons with the opposite helicity, because this got to flip from 129 to plus, from minus 129 to plus 129. So you're going to need at least 260 photons. Of course, you're going to have many, many more, probably losses and so on. Okay. You can learn more about this in these articles, and I thank you for your time. I'm 4%.
When you mentioned about the generation of second harmonic layer, what's the typical efficiency that you get?
Yeah, you're asking the wrong person. I mean, yeah.
No, I was just wondering. I can continue the question. So
Yeah,
come up here. I was just wondering if you would observe the reverse process, the down conversion. The up conversion efficiency is very small, then it's hopeless that you are going to see anything.
Yeah, it's typically small, although, I mean, this people measure this, and there is one exercise where they did the film with urea. Urea is supposed to be able to do it in the bulk. And in the simulations, it looks like the surface contribution is of the same order. So it's of the same order as in the bulk. So it's as efficient, let's say, as just the bulk itself.
But in that material.
In that material, of course, urea
It's probably much lower than the crystals that we usually employ to do second.
yes. Indeed. This is, I would say this is an interesting physical measurement, but for applications, as far as I understand, this is not fun.
For myself. Yeah. So when I didn't quite understand. So when you take your cavity and you place their molecules, okay, if you have many molecules, it's you're saying that you have like a system which has a tensor.
It was hundreds of nanometers, but it doesn't matter. But it could be tensor.
So my question is, if you have such a large system, do you need to understand the microscopic details of the molecules? So can you just say there's an effective index of refraction?
Yeah, potentially you can do that. Let's go back to notes. Potentially you can do that, I would say. The thing is then, the question then comes is, okay, how do you do that? And do you want to put it anisotropic, as checking really the what happens in the crystal, or how do you do the by anisotropy?
But you're treating your molecules as just a dipole object.
It's a dipole object, but the couplings between them. So when you put them close together, then there is this effect that you have to find all the couplings from all the cells, and what we call the effective T matrix, which is the T matrix of the object embedded already in this environment, is rather different. The dipole can rather change with respect to not having it in the lattice. Yeah, so I mean, what you said, yeah, because see, the thing is that they're very, very close together. So it's not okay to just say, okay, have one and then the other ones don't see it. This is okay in the other, when you have this, whoops. This is full quantum mechanics, so this whole thing is correctly accounted. And then what we neglect in this case is the interaction between this one and this one. In this case, we're actually doing exactly what you said, because we compute the refractive index, also using BFT. And then you assume, okay, we forget about all the details. But in the other case, for example, if you do something that is isotropic, then you wouldn't see these two different lines. And do it to some extent what you say, but not for all the systems.
One question. What are the catching invariants in these conformal transformations that you have been?
All right, helicity is one. This doesn't change ever. And then the others, I have the paper where they explain. I look at them, this is mathematical papers, and it's not clear what they mean. There is linear combinations of generators of the Poincare group, multiplications of them, some squares, and it's not obvious to say which ones they are. It's a very good question. I'd also like to understand them myself. I know one. That's all. But they're written down, so it should be something visible. Only that, yeah, it's not obvious that you, I mean, you lose a lot of intuition. Okay, I lose intuition even going to Poincare. So when you lose a lot of intuition, it's not easy to see what this actually means, but it's certainly something worth researching. For example, it's not, I believe it's not one of the list, but there is something that you can do. You can define, this is what Baruch did, conformal invariant mass. So, okay, so one of the things is saying, well, mass is not conformal invariant. So mass is something is a length in for space-time, so it's invariant under the Poincare, but it's not anymore conformal invariant. And it's true. But then this person said, well, the same way that we took the mass before Einstein and we did something and now this is invariant, this Poincare, we can do an extra step. And he writes down how to actually do this to make something that you can have a mass parameter, for example, in the Dirac equation, but if you transform it accordingly, it's conformal invariant. I think it's interesting.
Any questions, Antonio? Yeah.
You said that one of the requirements of the transformation is that you keep the photon number invariant. I think it's true because you are dealing with inertial transformations. So if it was like a transformation non-inertial frame, then
yeah, indeed, it's there is this effect. I think yes, yeah, indeed, and those transformations are not in this group. And actually, there was a big debate for decades. I guess not very intense, but for decades of whether these special conformal transformations were accelerations. But I believe Kastrup has the definite paper. You look at that, you read it, and you see, okay, they cannot be accelerations, and this is all something else. But yeah, you're right. These are inertial transformations. Okay, inertial. I don't know what those special conformal transformations are, okay, but they are not accelerations.
Okay, so actually Ivan is going to be here until tomorrow afternoon. So if you want to talk to him, he's in my office this afternoon. Thank you, Ivan.
¿Cómo te va a las 3? A las 3, vale. ¿Estás ahí en el... Sí, ya lo encontré. ¿Tú vas a estar con él? Sí, estoy en su despacho. Después de yo...
Va a ser más fácil que yo te encuentre aquí. Que también es que está escondido, pero vamos. Vale. Vale, venga, perfecto. Te busco y hablamos.
Vale. ¿Cómo estás?
Bien, bien, ¿y tú?
Bien.
Oye, ¿quieres estar ya?
Ya me envió un mensaje.
Sí,
Ya. Pero ya tiene su cosa de...
Sí, es lo que me ha dicho. Que bueno, tengo que ir hasta allá. Es que mi no falla. Sí. En fin, a ver si te veo uno estos días, entre hoy y mañana. Sí, a ver si me paso ahí por...
Pásate y hablamos, vamos a tomar un café o no sé.
Perfecto. Me da gusto verte.
Encantado de verte.
Adiós,
Chao.
Primero, sean de plan. No sé. Y además, te digo, si dispara con el ahorita, que es mejor 1000 o 30. Pero además que no es lo que es la verdad. Muy bien. Muy bien.
Voy a hablar más de esto del biphoton Hilbert space, pero digo,
Bueno, ya acabamos de.